Welcome. In this lecture, we will continue our discussion with virtual memories and caches. We will start with a bit of recap from what we discussed in the last class. So, particularly we will start by discussing a bit again on virtually indexed physically tagged caches. We had said last day that the problem with physically indexed physically tagged caches was that the TLB comes in the critical path for cache accesses. So, therefore, cache access latencies are high because the TLB comes in the middle and we cannot access the cache until the complete physical address is generated. To do away with this, to improve the situation, so virtually indexed virtually tagged caches VIVT caches were proposed, and there what happened is that both the indexing and tagging of the cache was done based on virtual addresses. Okay. So, the logical address was used for both indexing and tagging of the cache. Now, this avoided TLBs to come into the critical path. So, TLBs are no more coming into the critical path. However, the problem again was that both the indexing and tagging, because it is done with logical addresses, it has no connection with the physical address and where a particular cache block is placed in physical memory. So, the issue is that now the advantage of VIVT caches is that, so I do not have to go into the TLB. So, even if there is a miss of the TLB and I have to go to the memory to bring in the physical page number, even that is avoided, and we do not need to go into the we do not need to go into the TLB for that. If the data is in cache, we are fine, we are happy. So, we do not go into the TLB to look for the physical address at all. However, the problem, as we said, is that virtual addresses have no connection with physical addresses. So, a particular data in cache is now stored only with respect to what the logical address says, and the logical address of different processes may be same. The physical address, so multiple processes have different physical addresses. So, the data corresponding to multiple processes will be stored in different locations in the physical memory. So, when I have the cache that indexed and tagged based on physical addresses, I do not have the problem that the same cache block can be stored in multiple different locations or multiple different sets in the cache. The same cache block cannot be stored in multiple different sets in the cache. So, the same block in physical memory cannot be stored in multiple different sets in the cache if I am indexing and tagging the cache using physical addresses. However, because these are virtual addresses, so a block in physical memory can be stored in multiple different locations or multiple different sets in the cache. And this is a problem because the same virtual address can mean different physical addresses by different processes. Okay. So, therefore, the same physical cache block may be stored in different locations, and therefore, the cache needs to be flushed every time there is a context switch and a different process comes into the CPU. So, when one process is executing on the CPU, for that for the virtual addresses of that process, I am accessing the cache using virtual logical address of that process, and now when there is a context switch, a different process comes in, and there the virtual address will mean entirely different set of physical addresses, and therefore, the previous entire cache the cache needs to be flushed, and there can be a lot of cold misses. That means, the previous data is all rubbed is all deleted from the cache, and therefore, when the new process comes in, I will have nothing in the cache, nothing of the physical memory in cache, and therefore, I have to repopulate everything in the cache corresponding to that process, okay, and this will lead to a lot of cold misses, as it is called. Okay, because the cache is cold and I will cold or empty, and therefore, I have to bring in data from the physical memory into cache. And so, that was the problem of virtually indexed, virtually tagged caches. Now, virtually indexed, physically tagged caches was a compromise between these two. So, in virtually indexed, physically tagged caches, what do? We index both the cache and TLB concurrently using virtual address bits. Okay. So, the virtual page number part of the virtual address is used to used to search the TLB for a hit. So, the TLB is fully fully associative, and so therefore, all the entries in the TLB will be searched for the virtual page number, and if the virtual page number is found, the corresponding physical page number is taken. Now, concurrently I will use the physical page offset, the virtual page offset, which is same as the physical page offset. So, the physical page offset will be used to index the cache, and if there is if the physical page offset matches, if the physical page offset I will use the index to I will go use the physical page offset to index the cache, and then corresponding to that I will try to match the tag at that particular location, that particular block, or a particular set of blocks in a set for a match of the physical page number that I got as output from the physical page number. So, here my TLB has produced a physical page number. From here I am indexing the cache. So, I have gone to a particular location and found a certain tag, and that tag I have obtained. If this tag matches with the physical page number, then I have a cache hit. So, why this is a benefit? This is a benefit because the cache and the TLB is accessed concurrently, not sequentially one after another, but concurrently, and therefore, I save time. The TLB does not come in the critical path. However, if there is a TLB miss, this access still has to wait, to get the physical page number from memory back, and then only we can have check for a cache hit. So, therefore, this strategy is helpful when there is a TLB hit. So, on an average it reduces access times with respect to virtually indexed, virtually tagged with respect to physically indexed, physically tagged cache, because the TLB and cache are accessed concurrently. With respect to virtually indexed, virtually tagged cache, it is not as efficient when one process is running, because if there is a TLB miss, I have to go to the physical memory. However, if there is a TLB hit, I have I can check for the cache hit without going into the physical memory, and I save time. But however, this approach avoids the need to flush the cache on a context switch. Okay. So, why? Because the physical page offset and the virtual page offset are same. Okay. So, therefore, when I am accessing the cache with the page offset part only of the virtual page number. So, this is the complete virtual address, and I am accessing the cache only with the physical page offset part. I am indexing the cache only with the physical page offset part. If I am doing this, then what essentially is happening is that I am basically indexing the cache using physical addresses only, because the page offset part of the virtual address and physical address is same. So, if the cache is accessed only using the page offset part of the virtual memory, then what happens is that, let us say I have the page offset of 12 bits. So, the page size is 4 KB, and let us say my cache block size is 128 bytes. So therefore, I have 8 into 4, 32 cache blocks, 32 blocks per page. I have 32 blocks per page. Now, each of these 32 blocks will go to a particular location in the cache, depending on what. So I have 128 bytes. Okay. So, I have 128 bytes is the block size. So, this will require 7 bits, this will require 7 bits, and therefore, so this will require 7 bits, and the other 5 bits will tell me where it will go in the cache. Okay. So, the cache is no more than 12. So, the cache is also 4 KB in size. The cache is 4 KB in size, and I know depending on what the other 5 bits are. So, 7 bits, the lower 7 bits are for accessing the cache, and the higher significant 5 bits will tell me which particular block in the cache this cache block is going to go. Which particular line in cache will this particular cache block. So, these 7 bits, each enumeration of these 7 bits will identify a particular cache block, and this cache block will go to a designated location or designated line in cache depending on the value of the more significant of the higher significant 5 bits. Now, therefore, each cache block will have a designated location in cache, and the cache block cannot be located into multiple locations in the cache depending on means irrespective of what the virtual address is, because the physical page offset and the virtual page is same. When the situation changes when we want to increase the size of the cache. Now, when we want to increase the size of the cache, then I need to use a part of the virtual page number, this part of the virtual these many bits, let us say these are 3 bits. So, in addition to the 12 bits that I have, in addition to I was using 12 bits. Now, in addition to 12 bits, let us say I use 3 more bits from the virtual page number to index the cache. Why? Because my cache was of size. So, I had 12 bits. So, 12 bits can access any one of 2 to the power 12 locations. So, any one of 2 to the power 12 blocks it can access, barring the byte offset again. So, okay. So, it will the page of, so I will need few more bits, I will need 3 more bits, 3 more bits I have used to increase the size of the cache. Now, what is the problem that this has brought into? Now, a particular cache block, a particular block in physical memory can sit in multiple locations in the cache. Why? Because these 3 bits will now depend on what the virtual address says. This previously what was happening, I was only using this physical offset part of the cache, and therefore, when I'm appending it to the physical page number and the physical page offset, I know that corresponding to this physical address, my cache block will sit in a particular set or particular block in the cache only. Now, these 3 additional bits have created this problem that for a given physical address, depending on what the values of these 3 bits are, the same cache block, the same block in physical memory can go into different sets or different blocks depending on what type of set associative or direct map what it is. So, let us say if we have a set associative cache, and therefore, the index part will tell me which set in cache my particular physical physical block will go into. Now, this page offset part remains same, but these three bits become different. Now, these 3 bits, therefore, this what happens due to this is that 2 to the power 3 or 8 different location, 8 different sets. Okay. Now, these 3 bits mean 8 different sets for a given this part remaining same, this part of the address remaining same, even the physical page number remaining same. When the physical page number remains same and this part remains same, that means I am going to the same physical address, I am trying to access the same physical address. However, depending on what the value of these 3 bits are, the same physical address. So, the block which contains this physical address can go into 8 different sets in the cache. So, I will reiterate, based on this physical page number and this page offset, let us say a situation in which this physical page number is same and the physical page offset is same, and I am trying to index the cache using this index. Now, this part of the index is going to remain same for this physical address. However, for the same physical page, the physical page number could be different. Sorry, the physical for the same physical page number, depending on what these 3 bits are, the same physical block can go into 8 different sets in cache. And this, as we had told, is the synonym problem. And one of the ways in which we had discussed 3 ways, today I will just recap the last one. One of the ways to handle this synonym problem was page coloring. And we said, what was page coloring? It is to restrict virtual page to physical page frame mapping in OS. We will restrict virtual page to physical page frame mapping in the OS. So, how will we do this? We will try to make sure that the index that the virtual address produces, okay. So, virtual address meaning this one, this entire thing is basically part of the virtual address, okay. Okay, this is the virtual address. So, that is why it is a virtually indexed cache. So, this is part of the virtual address. So, the index that the virtual address produces, we will try to make it same as if the physical address, equal to the index that the physical address would create. And how will we do that? We will do that using a scheme called page coloring, in which all physical page frames are colored. So, how are they colored? So, now the physical memory, if we see, let us say this is the physical memory, and this one is, let us say, the pages in it. These are the pages in it, physical memory, and these are the pages in it. Now, this one will require what? One, this page offset. So, page offset will address each location within this page. Within each page, the page offset can locate. Now, which page will be given by the page number? Okay. Now, let us say we colored the physical memory into 8 colors. So, coloring means I will give a unique ID. So, let us say this one is given 000, this one is given 001. So, 010, 011, 100, 101, 110, 111. So, I give 8 different colors. So, now again for the next set of pages, I will again give colors to it, 000, 001, 010, 011, 011, and likewise it will go on. Okay. So, I will go and color each page in the physical memory. So, statically before in the system, I will know that this page has color 000, page 2 has color 001, page 3 has color 010, likewise, and again this one will have again color 000, this one will have again color 001. So, for each page I will know what is its color. Okay. Now, what will I do is that, so each cache block within this, So, the page will be composed of a integral number of cache blocks. So, in this particular page there will be a number of blocks. So, not cache block, but number of blocks. So, each page again will have a number of blocks, like we had said in the previous case that our page was composed of 32 blocks. So, each page had 32 blocks. Now, here all these blocks will have a color of 001. All these blocks in physical memory within this page will also have the same color as the page. So, now for each block in physical memory I know what color it is. Okay. Now, I will use this scheme. A physical page of one color is mapped to a virtual address by the OS in such a way that a set in cache always gets page frames of the same color. Now, a physical page of one color is mapped to a virtual address. So, this physical page will be mapped to a virtual address. Okay. Now, if this page I will always map to a virtual address such that those 3 bits, these 3 bits in A, these 3 bits will also have 001. Okay. So, this physical page will be mapped to a virtual such a virtual address such that those 3 bits in A of the virtual address will be 001. Okay. Now, what happens if for this virtual address, therefore, I know that those 3 bits will be 001. So, the virtual I am restricting what? I am restricting during the mapping of the physical. So, for a virtual address I will map a physical page frame. Now, when I am doing this mapping between virtual address to physical address, I will map such a physical page number to a virtual page number that in that virtual page number those 3 bits of A will be 001 if this is the physical page I am referring to. So, only those virtual addresses will be able to get these physical page frames if that virtual address or those set of that virtual page number. So, this page number will be given to such a virtual page number in which those 3 bits of A will be 001. So, by this scheme I will always be able to ensure that this page will go to the same set in cache. So, when this page goes to the same set in cache, I will be able to avoid the synonym problem. Now, we will quickly study page replacement and go and look at page replacement again, so that we discuss one more important problem, which is Belady's anomaly and progress from there. So, we had already told why page replacement is required and to reduce page fault rates, and we said what reference string R is. So, these are the set of pages that a processor is accessing. Then we discussed different page replacement policies. The first one we discussed was first in first out, in which the oldest page in physical memory is the one selected for replacement. So, the oldest page in physical memory at any given time is used for replacement, and we discussed this. We will discuss again with respect to Belady's anomaly. So, I am not going into first in first out. We will look at FIFO issues again with respect to Belady's anomaly. So, I will not going into this again. For optimal page replacement, we said that we replace the page which will not be referenced for the longest time in future. So, I will have to know using an oracle as to which pages will be accessed in future. This is not possible, and hence this optimal page replacement policy is not realizable in practice, but we use this to measure or evaluate and compare other algorithms against how good it is. Because we cannot do better than the optimal, we will use it to compare other algorithms with respect to this one. Then we came into least recently used, and we said that in least recently used we replace that page in memory that has not been accessed for the longest time in the past. So, at any point in time I will the page frames, which page frames will be contained, the pages in the physical memory will be the one which is most recently used. So, the least recently used one will be replaced when I need to replace a page. So, when I need to replace a page, when do I need to replace a page? When there are no free frames in memory, and to get a new page into the physical memory, I have to replace an existing page in the physical memory, send it to the secondary memory if it is dirty, and then bring in a new page. So, we said that LRU was is the optimal algorithm, is an optimal algorithm when with the restriction that I can look back in time, but I cannot look forward. That means, this is practical because looking back is possible, looking forward in what will happen in future is not possible, but what has happened we already know. Therefore, looking back in future, this is the optimal algorithm. Why? Because it always keeps the most recently used pages at any given time. So, we looked into least recently used, so I will not go into that anymore, but we will study what were the problems with we also saw this, what are the problems with LRU, and we said that the problem was in practical implementation. Why is such a thing, why is it difficult to implement in practice? Because at each point in time for each page in the physical memory, I have to keep when it was accessed, because I am evicting the page, I am replacing the page which is least recently used. So, I need to know among all pages in physical memory which one is the least recently used. So, what is the logical way of doing that? I will have to keep a global clock, and whenever memory is being accessed, I will take the stamp of the global clock and put that stamp on this physical page. So, when I need to evict pages, I will have a time stamp associated with each physical page in memory. Whenever the page is accessed, I provide it a time stamp, I provide the time at which it was accessed, and therefore, I will know which one among all the pages in physical memory, which one was least recently used, which was accessed farthest back in time, and that will be evicted. So, this has a lot of hardware cost, because and also overheads, because at each access I have to update the value of this timestamp corresponding to that page, and this is hard. So, anyhow the solutions are this. So, I keep the hardware clock ticks on every memory reference. So, this keeps global time. So, with respect to memory reference, for each memory reference irrespective of which process does this reference, I keep a global clock, and I go on incrementing a global clock. Now, the value of this global clock is the timestamp which is attached to a page whenever it is referenced, and the page with the smallest time value is replaced. Now, this is a very costly solution, as we said. A simpler solution is this. We keep a stack of references, and this stack is maintained as a doubly linked list, and on each reference to a page we what do we do? So, when a page is referenced and it is found in physical memory, it will be in a certain position in the stack. So, I take that take this reference, this page, the node in the stack corresponding to this page, I take it out and put it on the top of the stack. So, this will require the updation of just 6 pointers. And now, at any point in time, because whenever a page is being accessed, I am taking that page out and putting on top of the stack. Now, what is happening is that when I need to replace a page, the page which is at the bottom of the stack is the least recently used one, and that is replaced. So, both techniques require additional hardware, and memory, because memory references are a very frequent phenomena, it is the overhead the overhead, if we implement it in software means whenever there is a memory reference, I have to go to the OS and update. Either I have to do a stack operation or I have to do a more costly continuously. I have to do a or I have to update the timestamp corresponding to that page. Now, in the first approach, when I am using counters, what happens is that when I need to replace a page, I have to search all my timestamps corresponding to all pages to find the page with the least value of the timestamp, which is very costly. Now, when I am using a stack, at each memory reference, I have to take that node from the stack and put it on the top of the stack. This one has a slightly higher overhead possibly than the counter one. That means just updating the timestamps. But when I need to replace a page, the stack is lower overhead. Stack has lower overhead. Why? Because we don't need to search the all pages in physical memory to find the least timestamp page. That I do not need to do. I will just go to the bottom of the stack and evict that node out. Okay. So, during the replacement, stack is better. However, for both I need to implement both stack and this counter one in hardware memory. So, both these techniques therefore require extra hardware. As memory references are a very frequent phenomenon, it is impractical to invoke the OS on every memory reference. So, if I do not implement this counter method or the stack method in hardware, I have to implement that in software, meaning that whenever there is a memory reference, I have to go to the OS and update data structures, which is also impractical because memory references are a very frequent phenomena. So, therefore, the exact version of ALU is not often used, and instead approximate ALU is commonly used. So, one of the most common implementations is to use an approximate version of ALU, which uses reference bit in the page table for each page. So, how does this operate? On a reference to a page, this bit is set to 1. Okay. So, each page has a reference bit. When I am referring to this page, when I am accessing this page and this page is in memory, I am setting this bit from 0 to 1 if it is not already 1. Okay. Now, and I have time periods or frames or intervals. So, fixed size intervals, after which I check for the after which I set the bits of all pages. I set the reference bits of all pages to 0. So, when at the start of a time interval, I set the reference bits of all pages to 0, and then within that particular interval, every page that is referenced, their reference bits are set to 1. And then when a particular page has to be replaced, I will try to use a page for which the reference bit is 0. So, a reference bit is 0 means that in the current time interval, it has not been accessed. That means it is of higher probability that this page will also not be used in the recent future, because it has not been used in the current timestamp. This anyway does not mean that this is the least recently used, but it is an approximate LRU. To avoid the high hardware cost of LRU, I just keep one reference bit on each memory reference. If that reference bit is 0, I set it to 1, and during replacement I try to find a page for which the reference bit is 0. That means which has not been used. It is with the approximate assumption that this is not a very frequently used page, because this has not been accessed in the current time interval, and therefore, this one could be a good page to replace. Okay. Now, if all bits are same for a given reference bit, suppose I find out among all pages for which the reference bit is 0, I may like to select the one which has which came into memory at the earliest, that means first in first out. I use FIFO for a given value of the reference bit. So, if I get a set of pages with reference bit 0, I can choose the one which came into memory at the earliest. Okay. So, that will be evicted. So, among all pages which have the same reference bit, I use the FIFO strategy to find out the page which needs to be replaced. The next one is sampled LRU. Sampled LRU is an extension over the approximate LRU which we studied using just one reference bit, and it has a slightly higher hardware cost in that the first byte of each page is used by this strategy. Now, what happens is this, that instead of in addition to the reference bit, I have a reference byte for each page. So, the first byte of a page will be used as a reference byte for the page. Now, at set time intervals, I have similar time intervals as was for the simple approximate LRU. I have similar time intervals, and we take an interrupt and get the OS involved. So, at the end of each time interval, there what I was doing, I was setting all the reference bits to 0. Here additionally what I do is I get the OS involved, and what does the OS do here? The OS reads the reference bit for each page. The OS reads the reference bit for each page, and the reference bit is stuffed. So, at the beginning byte for the page. So, in addition I already have the reference bits for each page. So, at the beginning of the interval I read the reference bit of each page and stuff it into the reference byte, and then all reference bits are again cleared, very similar to the previous scheme. This one is very similar to the previous scheme, the only difference being that before setting all the reference bits of each page to 0, I copy the reference bits of each page and stuff it into the reference byte, and then on a page fault I replace the page with the smallest reference byte. So, how does this scheme work? Now, let us say these are my reference bytes for each page. So, these are distinct pages, page 1, page 2, page 3, page 4, page 5, and this is the page table. So, this is the page table, and the page table contains my reference bits. These are my reference bits for these pages. Now, what happens is that now when at the end of, so what has happened is that here my time interval has come to an end, the current time interval. So, at the beginning of every time interval the OS takes charge, and let us say this one is the end of one time interval. There is an interrupt and the OS has taken charge. What does the OS do? It first throws these bits. So, these the least bits are thrown away, and what am I doing? I am stuffing all these bits to these places. Okay. So, I am stuffing these bits. So, when I have stuffed these bits, so see these bits here are the same as the MSBs here. Okay, as the MSBs here. Then I am clearing all my reference bits. Okay, I am clearing all my reference bits. Now, what happens? The values, this byte, if I take the numerical value of this byte, so I take this value of each of these reference byte, this reference byte. So, I take the numerical decimal value, say decimal value of this byte. Now, what does this decimal value tell? This decimal value tells me in the last 8 intervals what was the access pattern of it, and this MSB has the highest weight, meaning that it could be that in the last few intervals this page was not used, but this page was used immediately here. So, even if these bits are 0, I should keep this page. So, and let us say, so therefore, the numerical value of this byte tells me how good is this page for replacement. Lower the value of this byte, better is this page or candidate for replacement. So, I should replace a page having least value for this byte. Why? Because this byte tells me two things. A very low value of this byte tells me that this page was not accessed recently and this page was not accessed possibly many times recently. So, this page was not accessed very recently and this page was not accessed possibly not many times recently. So, this is what tells me the numerical value of this byte. So, I will replace that page having lowest numerical value of this byte. Again, for all pages having the same value of this numerical byte. So, having the same numerical value, all pages for which the numerical value of this byte is same, I will choose that page which came into the memory at the earliest. So, among all pages having the same value of this numerical byte, numerical value of this byte, I will use the FIFO strategy to choose for choosing the page which has to be replaced. So, we will now look at the clock algorithm or the second chance page replacement algorithm. So, it is an extension. It uses the reference bits in a different way. So, how does this operate? So, on a page fault it searches through pages, and then if the page's reference bit is set to 1, then it sets it to 0 and skips it. So, it gives this page a second chance. So, if it is 1, it does not it does not replace it, but it sets it to 0. Okay. Now, if a page's reference bit is 0, this is selected for replacement. If it is 0, then among all pages that is 0, I use the FIFO strategy to replace the one which has 0. Now, it searches, it starts the search from where the last search was left off. So, how does this scheme work? So, let us say the previous search ended with the pointer, that means the last page which was accessed was page 6, okay, which was accessed was page number 6. Now, this is the pointer to the first page to check. So, for all pages I have a circular linked list, and suppose the user references page number 4 and that is not currently in the physical memory. So, I have to replace to bring in page 4, I have to replace some page. So, last time the search ended just before page 6 in the physical frame containing page 6. So, now I will start from the frame containing page 6 P6. So, this one becomes the first page to check. Now, therefore, so first I find that the reference bit is 1 and not 0. So, I make the reference bit is 0 and I do not replace this page. Then I come to the next frame, this frame contains P1, the reference bit is 1 not 0. So, I only set it to 0 and go to and check the next frame. I come to the next frame, it contains page number 7 and the reference bit is 1. So, again I set it to 0 and I again proceed. When I come to the next page frame, I see that it contains page 3 and the reference bit for page 3 is 0, which means that in the current time interval page 3 was not accessed. So, therefore, I select page 3 for replacement, and after replacement I select page 3 for replacement and it goes to P4, page number 4 comes in page 3 and the reference bit again is set to 1, and then for the next search it now points to this page frame. So, my current search ended at this page frame and then my next therefore search will start from the next page frame. So, user references page 4, this is not currently page, we start at page 6, we check P6 then P1 then P7 and set their reference bits to 0, give them a second chance, and then check page 3 and notice that the reference bit is 0, and then we select P3 for replacement and set the pointer to P9 for the next search. Now, what is good about this algorithm is that if all pages are 1, then ultimately in the next round I will select this page. This one has a low overhead. Why? Because I am not searching for all pages which has a reference bit of 0. So, possibly which has a reference bit of 0, and I am going on searching for the next page which has a reference bit of 0. So, if all pages have a reference bit of 1, the search will circle through all page frames in physical memory and then come back to the first page for which the memory bit was set to 0 from 1, and it will be the one to be evicted. So, although this page is referenced, but I have been able to give a second chance, and because all pages have been recently used, I could not find a page with the reference bit 0, and I will choose that one for replacement. Now, one aspect which the second chance algorithm does not take care or ignores is that is this page dirty or not, has this page been modified, has been written to or not. If a page has not been written to, it is dirty. So, before a dirty page can be replaced, it must be written to disk. Before a dirty page has been replaced, it must be written to disk, and this has higher overhead. A clean page does not need to be written to the disk, and therefore, it has much lower overhead as replacement. I can just discard this page because it is not written, and therefore, it does not need to be written back to disk. It can just be discarded, and in its place a new page can come to. Okay. The page on disk is already up to date. So, we would rather replace an old clean page, old and clean page will rather an old clean page than an old dirty page. So, if both pages are old, I will choose one which is clean and which is not dirty, because I do not have to write that page back to disk. So, now we will go and see an extension of the modified clock replacement algorithm, in which we use the two bits, both the reference bits and the dirty bit. It is similar to the clock algorithm, but now each page, instead of having 2 states whether it is referenced or not referenced, will all have 4 states, whether it is referenced or not referenced, and also whether it is dirty or non-dirty. So, if a page has its reference bit 0 and its dirty bit also 0, it means that this page was not referenced in the current interval and is also clean. That means it is not, when replaced, I do not need to write this page back onto disk. If it is 0 1, it is not referenced but it is dirty. So, it is not referenced in the current time interval, but in the wherever it was last used, whenever it was last used, it was written to. Therefore, if I choose this page for replacement, I need to write this page first back into disk and then bring a new page. Then the next one is 1 0. The page has been referenced in the current interval, but is clean. That means I can discard this page. Okay. However, it was referenced, so it could be that it will again be referenced in the near future. However, because I have no one to replace, I may need to replace this if the other options are not there. So, and if it is 1 1, it is both referenced and then dirty. This one is the least preferred set of pages. If a page has the pages which have this 1 1 set, they will be the least preferred set of pages to be replaced. So, the order of preference for replacement goes from the one above. So, how will the modified clock replacement algorithm work? So, add a second bit to the page table, the dirty bit. Hardware sets this bit on write to a page, fine. The OS can clear this bit. Okay. Now just do clock algorithm and look for the best page to replace. So, what do? In one round of the clock, you try to find a page which is 0 0. Okay. And in this one, if you have for all those pages which are 0 1, you set it to 0 0. Okay. So if you have the least significant bit 1 in the first round, you set it to 0, and you go on looking for a page which has both bits 0. If you find a page which has both bits 0, you use it for replacement. If you see that if both bits are not 0, then you find out whether the least significant bit is non-zero. If the least significant bit is non-zero, you set it to 0. Fine. Now in the first round, if no page is found, then you try to find a page for which is you try to find a page which is then 1 0. So you go on making multiple passes in the order of preference, setting one bit to 0 at that time, and hence you may require multiple passes through the list to get to a desired page, to get the desired page for replacement. So now before proceeding, we will take a small example. Consider a computer system with 10 physical page frames. So I have 10 physical page frames. The system is provided with an access sequence A1, A2 dot dot up to A20, A1, A2. So pages A1 up to A20 are accessed one after the other, and again in sequence page A1 up to A20, where each AI is a distinct virtual page number. So each AI is a distinct virtual page number. Determine the difference in the number of page faults between the last in first out page replacement policy and the optimal page replacement policy. So let us first see what will happen in the last in first out page replacement policy. I have 10 physical page frames. So A1, A2 dot dot up to A10 will result in compulsory misses. So 10 page faults. So compulsory page faults, 10 page faults. Okay. Now A11, so it is last in first out. So last in is A10. So A11 will replace A10. A12 will replace, who will it replace? It will replace A11. Okay. And then there will be again these 10 page faults up to A20, So 10 page faults. Okay. Now after this, what do you have? You in the page frames, you have A1 to A9. So after this sequence, after this one is done, you have, after the first set of 1 to 20 references, you in the physical memory, you have pages A1, A2, A9 and A20. This is what you have. Now therefore, the next set of 9 accesses do not result in a page fault in the LRU, in the last in first out page replacement policy. These will be hits. So this will be page hits. This will not be page faults, these will be hits. Now A10 will again result in a fault. Now who will A10 will be who will it replace? So this is a last in first out page replacement policy. So therefore A10 will A10 when it is accessed, it will be replaced by the one which came in last. Who came in last? A20, because A1 to A9 resulted in page hits, they were not brought in. So last in this system, that means in the set of 10 page frames that I have currently, this set of 10 page frames that I have currently, A20 is the last in page. So A10 will be again replaced by this one. So A10 will replace A20, A11 will again replace, A10 will again replace A10, and likewise A20 will result in a page fault and it will replace A19 likewise. So therefore, how many page faults will you have? You will have here, let us see, these are 10 page faults, again these are 10 page faults, and then from A10 to A20 you will have 11 more page faults. So, this one will be 11 page faults. So, for the last in for the LIFO strategy, you will have 31 page faults. For the LIFO strategy, you will have 31 page faults. Now, when you use the optimal page replacement, you see that this 20 page faults will still be there. In the optimal page replacement, these 20 faults will still be there, okay, because these are all compulsory page faults. Okay. Now, in the optimal policy also, when 11 comes, it will replace page 10, because it will see in future and find out whom to replace. Okay. It will find out that A1 and to A9 will be replaced, will be needed later. So, it will go on replacing them. Okay. So, in a similar way as the LIFO strategy, it will also do the same, and at the end of the first 20 accesses, it will also have the optimal policy will also have A1, A2, A9 and A20 in the memory. Okay. Now, what will happen, A1 to A9 will be page hits. When A20 comes in, now which page will the optimal page replacement policy replace? It will replace any one of the pages between A1 and A9, but it will not replace A20. Okay. So, why will that happen? Because A20 it knows that will be needed again. So, A10, A11, A10, A11, A12, these when this will be accessed, it will go on accessing these one, it will keep A20 in the memory, so that when A20 is needed again later, it will be found in the physical memory. A20, the access of A20 will not result in a page fault for the optimal page replacement algorithm, because it has an oracle to know which page will be used in future. Okay. So, A20 will not result in a page fault, and therefore, the optimal policy will incur only 30 page faults. So, the question, determine the difference in the number of page faults between the LIFO page replacement policy and the optimal page replacement policy. The answer will be 1. The difference is 1. Now, we go on to understand one aspect of page replacement, which was important for which is important from a theoretical perspective, and also because this was quite a concern for early page replacement replacement policy designers who used FIFO for their replacement algorithms. So, the people who used FIFO encountered an anomaly which is popularly or commonly known as Beladi's anomaly. Now, what is this? Let us say that you have 3 page frames. Let us say you have 3 page frames in memory. Okay, your whole memory consists of only 3 page frames in one situation and 4 page frames in another situation. So, in one case you have a system containing 4 frames in memory, and in one case you have 3 frames in memory. Now, sometimes it so happens that for example, for this reference string, it so happens that FIFO replacement, for the FIFO replacement policy, when you have lower number of frames in memory, you will have lower number of page faults than when you have more number of frames in memory, you will have more page faults. Now, this should not happen, right, because you have more space in physical memory. When you have more space, 4 frames in physical memory means that you have higher space, the capacity of the physical memory is higher than when you only have 3 frames in physical memory. Okay. So, the capacity of the physical memory is higher, but you still are incurring higher number of page faults. So, this is an anomaly which is referred to as Beladi's anomaly. Now, we will try to see in more detail why this happens. Now, the reason for Belladie's anomaly has been found to be this: pages in memory at any given time for the stipulated number of frames is not always a subset of the pages when the number of frames become higher. So, why does Belladie's anomaly happen? Because suppose I have 3 frames, at any given time the frames, the pages that are there in memory is not a subset of the pages that are there when my number of frames are higher. So, when my number of frames are lower, if the pages that I am containing are not a subset when my number of pages are higher, then Belladie's anomaly occur. We will take an example, we will take the example of this reference string and see why and how this happens. So, these are the set of memory references, and these are the set of memory references shown here: 1, 2, 3, 4, 1, 2, 5, 1, 2, 3, 4, 5. So, these are the references shown here. Now, at time 0, so this one is time 0, time 1, time 2, first reference, second reference, third reference, fourth reference, like this. So, ref hash, this one is 1, 2, 3, 4, like this it progresses. So, at the first reference, so I am bringing in page 1 to frame 1, and what happens is that it comes to frame 1 and frame 2 and frame 3 are empty. So, there is a page fault. Then 2 comes in and goes to the second empty frame. The frame 2 is empty and 2 goes here. For the third reference, 3 comes in frame number 3. For the fourth reference, because I am using a FIFO policy, first in first out, so 1 was first in, so 4 replaces 1 and it again incurs a miss. Now, 1 comes in, now 1 has already been replaced in the previous access, so 1 again encounters a miss and it replaces 2. Now, 2 is accessed again, 2 again incurs a miss because 1 has replaced 2 and therefore it replaces 3. Then 5 is accessed. Now, 5 incurs a miss. So, the first in among these 3 pages is 4. So, therefore, 5 replaces 4 in frame number 1. So, then what happens? Then we find that 1 comes in and 1 is already there. So, therefore, this is green and this is not a miss, this is a hit. Then 2 comes in, 2 is already there in frame number 3. So, this is again a hit. Then 3 comes in, however, 3 has been replaced and because 1 is currently the one with the which is earliest, which came into the memory earliest. So, 3 is replaces 1 and then 4 comes in and 2 is now the one which is the earliest one which has come into memory. So, 4 replaces 2 and then 5 comes in, 5 is already there in memory. So, this one is a hit. Now, when I have 4 frames in memory, these are the set of accesses. Now, what has happened? See, so 1 comes in, miss, 2 comes in, miss, 3 comes in, miss, 4 comes in, miss, then 1 comes in, 1 is a hit because it is already there, I do not need to replace. 2 comes in, 2 is already there, it is a hit, is not a miss. Then 5 comes in, 5 replaces 1 because 1 is the earliest one which came in, it is in the FIFO order, 1 is replaced. Then 1 comes in, 1 is then 2 is the one in the FIFO order which needs to be replaced. So, 1 replaces 2, then 2 comes in, 2 replaces 3 and then 3 comes in, then 3 replaces 4 and all other accessors are miss. Now, we see that when you have 3 frames in memory, the number of page faults are 9, you have 3 hits. Okay. And when you have 4 frames in memory, you have only 2 hits. So, therefore, you have 10 page faults. Here you have 9 faults and here you have 10 faults. Now, let us see why this has happened. If you see what has happened. So, at this position I have 5, 2, 3, 4 in the 4 frames, and here I have 5, 1, 2. Now, 5, 1, 2 is not a subset of 5, 2, 3, 4. Because 5, 1, 2 is not a subset of 5, 2, 3, 4, when 1 is accessed. So, when 1 is accessed, 1 is there in memory here, but at this point in time 1 is not there in the physical memory when I have 4 frames. So, I have a miss here when 1 is accessed, but I have a hit here when 1 is accessed. Why? Because if you go back to the definition again, the pages in physical memory at any given time. So, these are each different times. At any given time, the pages in physical memory for a stipulated number of frames. So, pages are, so for 3 frames, for a stipulated number of frames 3, is not always a subset of the pages that are there, when your number of frames become higher. When your number of frames become higher, the pages are not a subset. For example, here 5, 2, 3, 4 is not a superset of 5, 1, 2, and therefore, for this case 1 is a hit and for this case it is not. For the same reason again 2 is a hit. So, this 5, 1, 3, 4 is, so 5, 1, 2 is not a subset of 5, 1, 3, 4, and therefore, is this one was a hit here, but this resulted in a miss. Again in this case 5, 3, 4 is not a subset of 4, 1, 2, 4, 1, 2, 3, and therefore, when 5 is accessed here 5 results in a miss here, however, 5 is a hit here. Okay. So, Bellatti's anomaly occurs because pages in memory at any given time for a stipulated number of frames is not always a subset of the pages when number of frames become higher. Now, the optimal algorithm and the LRU, both the optimal algorithm and the LRU do not exhibit Bellatti's anomaly. The optimal algorithm always maintains the most frequently used pages to be accessed in future. So, optimal algorithm, what does it maintain? At any point in time, the optimal algorithm maintains the most frequently used pages, the most recently used to be used pages to be accessed in future. Okay. And this one LRU keeps the most recently used pages, most recently used pages accessed in the past. So, because LRU at any given point in time, whatever be the number of frames that are available, what does an LRU do? It replaces the least recently used page. So, therefore, what are the pages that are there in memory at any given time? The most recently used pages are there. Okay. And what does optimal algorithm keep? The most recently used pages that will be accessed in future. Whatever I have written here may not be exactly correct, but I am telling it that optimal algorithm will keep at any point in time the most recently to be accessed pages in future, and LRU keeps the most recently used pages accessed in the past, irrespective of the number of frames. So, irrespective of the number of frames, both these algorithms keep the most recently accessed pages. Now, most recently used pages. Most recently used pages for a lower number of frames is always a subset of the pages we have for a higher number of frames. Suppose I have a certain number of frames and at a given time I have a certain number of pages in memory. Okay. Now, the most recently, so let us say I am using the LRU algorithm. So, the most recently used pages will be there in memory for 3 frames Now, the most recently used pages at that point in time for 4 frames will always be a subset, will always be a superset of the most recently used pages if I have 3 frames. The most recently used pages for 4 frames will always be a superset of the most recently used pages for 3 frames. This is why Bellatti's anomaly is not there in the least recently used algorithm, neither is it there for the optimal algorithm. Now, we will go into another concept called page buffering. Now, page buffering, it is expensive to wait for a dirty page to be written out. Now, let us say during a replacement, I need to replace a dirty, I have to replace a dirty page. Now, it is expensive to wait for the dirty page to be written out. Instead, what we can do to get this process quickly started, we can always keep a pool of free frames. Now, these frames are free. How do we make it free? On a page, how do we do this business? On a page fault, we select a page to replace, okay, and then write a new page into a frame in the free pool. So, at any given time, I have a pool of free frames. So, there I can just close my eyes and bring a page into this free pool without looking into anything else. But how do I maintain this free pool? I will first choose a page for replacement. Mark the page table, restart the process after replacement. So, I have brought a page from the disk and put it into this free frame, but then I take this page which I have used for replacement and put it into the free frame pool. So, at any point in time, I have a kitty of free frames that are ready for replacement, and for the current access I am using a free frame from my free frame pool, but I am using a free frame. So, I will replenish that free frame pool by 1 frame after replacement. So, I will restart the process after replacement, and then I will quietly do my business of creating 1 more free frame. So, if the selected page frame is dirty, then after replacement I will put that page into disk and then put this page into the free frame pool. And because this dirty page was not put into the memory during replacement, this overhead is not visible to the page replacement. And this dirty page, by putting this dirty page into the disk, happens after the replacement and after the process has started. And when this process is working in the CPU, I am replacing this dirty page into the disk. I am putting this dirty page into the disk and creating the free frame pool. So, place frame holding the replaced page in the free pool. Okay. So, this is how buffering will work. Now, one more important aspect is that, one more enhancement that we can do with this is that when I am replacing, I may not just I may not destroy the contents of the page. I have put it in the free frame, I have done the replacement if required, but in the free frame let us keep the page intact, do not destroy the contents of the page. If that page is required to be replaced, in any case this page is clean and can be used because it is there in the free frame pool. But by chance, if this free frame, I have kept it in the free frame pool, but by chance let us say this page is accessed by one process. Now, I can keep a pointer that this page is still there, although it is there in the free frame pool, it is actually there in physical memory still now. It has not been replaced. So, I can access it from the free frame pool itself. So, I will get the page in main memory. I do not have to go to the disk to get this page. So, even if I put pages in the free frame, I will just keep a mark as to what pages are there in the free frame pool at any given time, and if they are accessed, I will be able to put use that page from the free frame and use that instead of going to the disk. Now, allocation of frames. Now, still now we are saying that a page does not matter, a page frames have no connection with the processes. Now, this is entirely not true. So, each process requires a minimum number of frames. So, typically what do we do is that we allocate a certain number of physical page frames to each process. However, this is done using many schemes. There can be a fixed allocation scheme, there can be a prioritized allocation scheme, and it has many variations. For example, the first strategy is the fixed allocation scheme. In the fixed allocation scheme, let us say I have 100 frames in physical memory. After these 100 frames are available after allocating frames to the OS, and I have 5 processes. So, the degree of multiprogramming is 5. I give each process 20 frames. I divide the frames into these 5 processes. So, this one will be called a fixed allocation. Otherwise, we can do a proportional allocation. I allocate fairly based on the process size. So, for example, let us say let Si be the size of process Pi, okay, and capital S be the total. So, size of the process Pi in say number of pages, and S is the summation of the pages, summation of the number of pages over all processes that are currently there, that are currently active, and let M be the total number of frames that are there in physical memory. So, then the number of frames that will be allocated to a certain process, to process Pi AI, the number of frames AI that will be allocated to process Pi will be given by Si divided by capital S into M. So, so I allocate a number of frames proportional to the size of the process. Okay. For example, let us say I have 64 frames in physical memory, and S1 has a size of 10 virtual pages, S2 has a size of 27 virtual pages that it requires. So, therefore, S1 plus S2 is 137. So, total number of pages summation Si is 137, and out of which S1 has a size of only 10. So, I allocate and let us say 2 pages out of this 2, this 64 minus 1 is 64 minus 2. So, 2 pages I am using for OS. So, out of these remaining 62 pages, I will allocate 4 pages to process A1, and I will allocate the remaining 57 pages to process A2. Why? Because P2, the process P2 has a much larger size, S2 equals to 127 pages. So, the number of frames that is expected to that this page process 2 is expected to require is much more than P1, because P1 has a much smaller size with respect to in terms of the number of pages. P1 has a much smaller size. So, I will allocate, when allocating frames, I will allocate P1 only 4 page frames, and I will allocate P2 57 page frames, because their sizes are also very skewed. Now, if I allocate the same number of frames, we understand that the memory the memory utilization will not be that good. Now, the next is priority based allocation. Now, priority based allocation is proportional allocation using priorities. Now, instead of sizes, I use priorities. So, if process Pi generates a page fault, select for replacement one of its frames is available. Otherwise, select for replacement a frame from a process with lower priority number. So, now what it does? So, I have allocated, let us say, based on proportion, I have first allocated the frames to different processes. Now, During replacement, if I have free frames allocated to this process, I do a local replacement. I will choose a frame from the frames, I will choose a page for replacement from the frames which are allocated to this process. However, if none of the frames are free, so if all frames allocated to this processes are busy, that means are allocated and no frame is free, then I will choose a frame, free frame from a lower priority process. So, I will take a frame from a lower priority process. Okay. This is the priority based allocation scheme. Now, after this we come to the concept, we understand the concept of thrashing. So, this we will continue in the next lecture.